I've done with people at Los Alamos and also at Davis, Michael Schneider. Really, and Michael's here. Michael's the one who's done all the work having to do with extending the Los Alamos work. And everybody's done work here except me, is what I'm saying. So, and I changed my title to Beyond Standard Parameter Inference. So first, I just want to review standard parameter inference, at least how I think about it, which goes like this. So you have your data, and you calculate some summary statistic that you can also calculate from your model. And you calculate an error distribution for this summary statistic. There's different possible ways you do this. Assume Gaussianity and do some forward Monte Carlo simulations to get the covariance of your summary statistic. Assume Gaussianity and do just cut up your data into subsamples and see how the fluctuations go across subsamples. You can apply exact Bayesian methods, which works it's practical in a very limited regime. After that, then you have to form a likelihood using the error distribution that you have and your measured summary statistic. And so you compare your measured summary statistic to your model summary statistic at many points in the parameter space. For example, doing this with running a Markov chain typically requires calculation of the summary statistic at tens of thousands of parameter locations. Then you take your Markov chain, and it's easy to process this to any desired marginal parameter distributions you want, like the probability of the scalar spectral index given your data, or whatever. So, what do we do if calculation of these summary statistics is very computer intensive? So the 10 to the fourth calculations is impossible. We can't have Andrew Zentner and his collaborators running 10,000 of these simulations every time. Also, what if the covariance of your summary statistics is parameter dependent? Then it won't work. You'll be getting things wrong if all your estimates of the covariance come from doing a forward simulation from one point in the parameter space. So if your covariance is parameter dependent, then what do you do? So this. What I'm talking about is attempting to address these challenges, and I think it's relevant for this workshop because it's relevant for lensing. Sufficiently accurate calculation of model 2-point and 3-point functions, for example, are very computer intensive. We may even have significant parameter dependence. This has been pointed out, at least in the galaxy power 2-point function, 3-point function case, that this covariance between the 2-point and 3-point functions seems to be significantly parameter dependent. I'm not sure how important this is, but in some sense, I'll say at the end, we kind of get this part for free out of our scheme. Another point is that the impact on the summary statistic means and uncertainties due to complicated systematic error sources is best understood by simulation. And certainly we have, in lensing, complicated sources of systematic errors. So here's a brief overview of the method, which kind of falls into three different chunks. First design, simulation design, which is deciding how do we. All right, so we have this parameter space we want to explore. Where do we want to actually calculate what our model predicts for, say, our 2-point function? How do we choose those points in parameter space? Secondly, having done that, how do we then know what the simulation would have produced at the points where we hadn't sampled? How do we interpolate? And also not only interpolate, but estimate and propagate any errors from interpolation. And then how do we tie this all together to do parameter inference? So first, design. So the goal here is to, so you have some high dimensional space. In this case, it's five dimensions, and you want to choose some sampling that when you project down to lower dimensions, you actually fairly uniformly cover all of these lower dimensional projections. You want points to be as spread out as possible in the lower dimensions. If you do that with a regular grid, you have these horrible projections where even though there's lots of different points in the parameter space, in any projection down to 2 dimensions, we only have one. In this case, 25 different points.
Sorry, I'm just going to mental blank. Why is that bad again?
Well, it's bad because if you're going to interpolate over this, you're going to do a lot better with interpolation if you have this measurement over a bunch, in a bunch of areas, different points, than if you have.
You interpolate in n dimensions.
You're interpolating in the n dimensions.
So in that case, isn't that okay?
Well, if there are, if there's some variation that's saying going with n, that's kind of higher frequency than the spacing, you're never going to catch it.
So I suppose it depends about how much how it varies in a direction in n-dimensional space. I don't know. Okay, well, if it varies, okay, I can't describe what I'm thinking. I'll come back to you later.
It depends on the function itself.
It depends on the function itself. Maybe you'll do fine with the grid.
But just think about a one-dimensional projection if you want to interpolate between points on the line.
Yeah.
Then projecting that sort of upper part, you've got a whole bunch of points to move through. On the lower part, you have fewer points.
So this is only relevant if something is.
Well, that's sort of if you
one
get
the
to the
parameters.
edge of your box.
The question is if you're projecting and analysing 5-dimensional things or two-dimensional subset. What you're saying you'll do it in 5D space.
Like, I'm just thinking of things which vary in 5 dimensions. You would have to do in 5 dimensions, and if it's only relevant to look at 2 dimensions at the very end anyway. So.
Right. So the interpolation is always done in the 5 dimensions.
Right.
So I'll grant you that I guess it's not just immediately obvious. So it's beyond the obvious.
If some of the properties are quite independent of 1 or 2 parameters, then this is very helpful.
Yeah, it's even if you
It helps you. If the action is definitely going to be more in some parameters than the others, and then so this is going to help you in that way. At the very least, I can say that, which is repeating what you said. So regular grid is potentially horrible, and another solution, better solution, is to use what's called an orthogonal array Latin hypercube sampling, and this is a fancy name. Most of the orthogonal array part of this is really simple, and that's to take. Let's say we have two dimensions here, and we just we're going to do 4 samples. We break up our grid like this, and we just choose locations where you've got you're making sure that you're not duplicating any of the rows here, right? So nothing is going to come along this way. Now I can't use any more of these. And in fact, so let's say I do this, then later I got to choose this.
It's more or less a Sudoku problem.
Sorry? Yes.
That's a short-term name.
So this is the orthogonal array part of it, and then from the points in the center of this, there's some adjustments made, which is some black magic that I don't understand that helps to lead so perturbations away from this that reduce some function of try to make these spread out as possible in all lower dimensional projections that you can have. That's the Latin part. This is the part I don't understand, right? Okay. So the second aspect, so that's the design aspect. And now the, let's see, where's the erase? There we go. I want to talk about the simulation aspect. So you choose your design points, you run your simulation there, and now you want to build basically a simulator of your simulation. You know, so you could figure out, well, what would be the answer at these points where I didn't run. And so let me just run through this. So this is called building an emulator. And so first, let's consider a really simple case. We've got one number that we're calculating, and it depends on one parameter. We'll call theta. And let's say we run our design at say these 5 points, and we get something out like this. And now we want to get a point here. Well, now this is such a boring curve I drew that the sophisticated interpolation we're going to do is really not worthy of this. But this is just to get the concepts across. So we want to know it here, even though we've only got it here. What we do, first thing we do is because the statisticians were involved in this, we remove all interesting physics from this by instead of modeling mu, which would be something with units, we model mu tilde, which is just subtracting off the average value of mu across the simulations and dividing by basically the RMS across the simulations. So just to scale this to something very general, has zero mean and unit variance across the simulations. This is just how this works in the formalism. And then we treat this mu tilde as something that's a sample from a normal distribution with zero mean and variance sigma that depends on theta and these parameters that control this covariance, and explicitly sigma equals 1 over lambda times, I'm erasing really important information here. Lambda rho to the 4 times theta minus theta prime. So that's so why this form? We also rescale theta so that this theta is just going from 0 to 1 here. And so if for half the so first of all, so what's lambda at theta at theta equals theta prime? So if we're just looking at the variance in one place, we've got that's just given by 1 over lambda. So 1 over lambda is the variance. Rho is basically giving us the strength of the correlation. If rho is 1, there's complete correlation across here. If and if we have
square theta minus theta prime, and then rho is the correlation between points separated by a half on that scale.
Right. Yeah, that's squared. Thanks. So okay, that's okay. So for points separated by a half, then the correlation coefficient is rho. So we just have this model for what this came from. So we model it as something that's drawn from this correlated Gaussian. And now we can actually use this simulation data to estimate what lambda and rho are. And so we can draw, we can calculate the probability distribution of lambda and rho given this data. And then we can also calculate P of mu given lambda, rho, and the simulation data. This is, lambda and rho specify this covariance matrix, and mu is this Gaussian. So this is actually, if we drew samples from this, we'd be drawing, the Wiener filtered curve through here, plus samples around that Wiener mean. So we could, this is how we can use this emulator, is actually to draw these samples. And so not only do we get, are we able to now calculate mu at points that are different from the design points, but we also have a measure of the uncertainty of this interpolation, which is the spread of the values of mu.
So how different that from a Gaussian approximation?
Sorry?
Sorry, I missed something. How different is it from a Gaussian approximation to the data? Because it's a...
It is a Gaussian. So
Okay.
so far we're just modeling. Say for example, this could be this could be the power spectrum. So for right now we're not doing it. Right now we're not estimating the errors in mu. So another thing that goes in here, right, is okay. Now I have some measurement of mu.
But you have some data, you compute the covariance matrix in your parameterization of your data. And
Simulation data, you mean?
Yeah, simulation
Right.
data. And then, so from that you determine the covariance matrix, and then you can sample from it, basically.
Well, we're determining a covariance matrix that's telling us about how these data are correlated from one point to another. Not the uncertain, the data points themselves. Not the. I haven't gotten to talking about the uncertainties in a measurement of mu, which I think maybe what you're talking about. Oh, okay.
Sorry, is this fundamentally making a linear assumption, assuming
No.
that mu is proportional to some Gaussian scatter of a linear correlation?
So this is just. I mean, this does not have to. This could be much more interesting behavior.
I don't see how your model describes that.
Well, this could be something that is very.
It's just
What-
saying
what-
the outputs of some set of simulations of mu are multivariate normally distributed.
Right. With respect to you fit the parameters.
And you fit the parameters.
So you can. I can't quite figure out what information you're putting in. I mean, where you put in the fact that the curvature of this correlation is not. Gaussian is very small number of parameters.
This we have a very specific form for the covariance structure, right? That it's going like the power law of the separation.
So that determines how smooth of a curve you're going to fit the unit points.
The smaller rho is, the lower the covariance, right? And so you'd be the smaller rho is that then you'd be able to have higher frequency motions through here.
So if mu is a power spectrum, you're assuming the power spectrum estimates are Gaussian distributed, is that
No.
underlying assumption?
So-
what is this exactly?
Let me
Can you give
let
an
me
example
go
later
on to
maybe?
explain. So let me go on and say what this looks like in the case mu is the power spectrum.
Yeah.
Okay, and then come back to that question. So that was one thing we're measuring as a function of one parameter. Now let's say we have multiple things we're measuring, like a power spectrum in different bands and many parameters. So then we'd write we would expand this into some principal components. So there'd be these various shapes in K, and the different parameters would pick these shapes up differently to have how this thing depends on the parameters. And now we would do exactly the same thing, except now we would treat this W as a Gaussian process. So is again a normal this time for so we have, yeah.
Right, so you've taken the variation of mu over the whole space, broken it into principal components,
Right.
and then done this interpolation scheme separately on each of them.
Exactly. Yeah. And now, Ramon,
Can you say what P mu is and what power is?
so this is just the number of components you keep. Okay, so you may have there may be 32 bands of K, say, but we only keep perhaps 5 components because that captures all the variation that we're seeing in our simulations. So this is some shape in K space, and at a given point in the parameter space, we pick up different amounts of these shapes. So we got say we keep 5 components. We've got 5 basic shapes as a function of K, and when you move somewhere in parameter space, all you're doing is altering the those coefficients. How much of which shape are you picking up? Now there'll be some error in this that I'll erase your name to fit in. And this is also so this can be measured because you have the full thing also, at least you're and this contribution to the error can be propagated as well.
Does that also mean you need fewer samples to estimate the covariance matrix? Is it more? Because that can be quite badly behaved, but perhaps the first few components,
Right.
components are better
Right.
behaved.
Right. You played around with that, Michael, and I think that.
That's true, but
Yeah.
he hasn't gotten it.
All right. So, and this is the basic procedure for building this emulator. And again, it is odd. I understand that we're using a Gaussian to interpolate stuff that doesn't look like what you get out of a Gaussian random field. But what comes out of the simulator is not. I mean, approximating what comes out of the simulation as a result of a Gaussian noise process doesn't make any sense in some way because it's a very non-Gaussian thing that comes out. But you can treat it as that, and it could be a very highly unlikely Gaussian realization. But you just condition. You say, given that it was, then what are the points in between? How do I get at the points in between? So it's just used for the interpolation. All right. So this here's a test of a design approach combined with the followed up with emulating the results to a CMB power spectrum estimation, CMB power spectrum calculation. So they took 128 points sampled in this standard 6-dimensional space, and then performed a test where you actually use just 127. You single out one point. You don't put that into the things being used to build your emulator. You use your emulator to predict what that point should be, and then you look at the result. And so here's percent difference. This is 0%, 1%, minus 1%, and multiple moment L going from 0 to 1,000. And from just these 128 points, there's actually a very good capturing of the behavior of C sub L over this parameter space.
So here, all the simulations, you have only one realization, and they all have the same random phases.
So here, what is the quote-unquote simulation? is actually a Boltzmann code calculation.
Oh, I thought it.
Yeah.
Okay, it's not unembodied.
Right.
Okay.
What are the ranges of the parameters?
All right.
The range of the parameters are for the WMAP3 1 sigma constraints on each of these. It's plus or minus 3 sigma around the best fit value. So this is
the variations in the CLs between your different parts are much greater than the residuals you're seeing here.
oh they're yeah.
Okay.
Oh yeah, they're huge. Yeah, and this is working this well, despite that there's an obvious improvement you could make. I mean, this is these are the probability is very correlated across these parameters, right? And you've just gotten this 3 sigma out in every direction. So most of this volume of the 6-dimensional space is just empty. None of that information went into the construction of this design.
Empty in terms of likelihood.
Empty in terms of probability, right?
Yeah. But they're all
You don't
legitimate
care about it.
cosmology.
But it worked anyway.
But you don't care. There's no, it doesn't matter if it's combination, right? Whether it's selection or not. It's just you define your parameter space and that's it.
Well, you could do this more efficiently, maybe even get down to fewer. It doesn't matter. You can run a Boltzmann code 128 times, and it doesn't.
But in your sampling, there is no likely information in your truth of this 128 point.
The only likelihood information is just that you're going out 3 sigma in each direction. Yeah.
And how many modes did you keep?
This was, I believe, 7.
So the variation in CL across the whole space is much more than 1%.
Oh yeah.
But what's the variation in the CLs between nearest neighbors in this space compared to that?
Right. That's a good question. I don't know.
And this doesn't depend which of the current Antonian you exclude. It's not that you were ranking everything.
This is a spread. So this is a summary of all the residuals. 50% of the residuals
okay, fine.
are smaller than this. Not
Fine.
are
Okay,
smaller
yeah.
than this. 90% are smaller than this. Yeah. Yeah. No.
You said you went after the 3 sigma points,
Right.
but you sampled uniformly between those
Yeah.
points. Now, do you think it would work better if you actually sampled from your trial?
Yes. Yeah. So that's what I was saying. Was that this is just terribly inefficient, full of no information, and
But in practice, you would sample from trial.
No,
I-
actually, wait,
Yeah.
so, I've played with this a lot, and I would change that now.
really.
So, these Gaussian process models, they do a terrible job of extrapolating. So if, for example, if this holdout point was at the very edge of this hypercube parameter space, these errors would be a lot worse. And they also, the conditioning, the building of the emulator doesn't work very well if you have a huge void in your hypercube. And so that's why this orthogonal array Latin hypercube works so well with its sort of space-filling design. That,
But I would do this, which is actually transform the parameters so that they're the identity matrix in variance, right? So that basically your probability looks like this. It's isotropic, and then go ahead and do the orthogonal array Latin hypercube sampling in your cube that fits around this, and then just throw out the points that are beyond the you know that are in these regions, and then you're not at. I mean, as long as this is going out to where the probability is really gone, then your boundary problem is taken care of.
I think what I'm saying is that I don't think you have a boundary problem if you really believe the result of your last experiment.
Right.
But what you don't want to do is have a denser set of simulation runs in regions of high prior probability.
You're one single error, so that's very bad.
No, but they're sort of wasted in a sense. You just need this sort of even volume sampling.
Yes.
So doing a denser set of sampling in the higher probability, and you're still going to be dominated by errors where it's sparser sampling.
Yep.
If you just wanted the best fit point, then it would be good. to do that, but because we want to have 68% and 95% limits on things,
Right.
then you actually want to focus the simulations on those contour regions.
So this is just to say that then you can propagate this through to parameter inference, as they've done here. The results themselves aren't interesting.
So
Is there-
sorry, just
It's not interesting. Go ahead.
Okay, so no, sorry, there's like a Ben van der Venden's scheme, right, to interpolate in n-dimensional space. So
Right.
it goes from- So how does it work? How would it compare from? I guess
At
it needs a very big training set, but if you were to use like as big a set of simulation to feed your emulator.
I talked about this, and Ben was in the audience, and I had said this worked really well. He had used many fewer simulations than Pico did. There's a comparison in this paper with these 128 points versus Pico using something like 10,000. But Ben objected and said, actually, you can use a lot fewer, and it doesn't get much worse. So I don't know. In some sense, it's academic in this case because you can easily do 10,000 instead of 128. But the CMB is not necessarily the killer application for this. It's when the simulations are harder to do.
To be fair to Ben, he also pointed out that Pico comparison done in this paper extrapolated Pico beyond where it was originally trained. And
So one thing though about this work where we got involved this was realizing that for this to be practically useful, we also had to use the simulations to tell us about the error distributions as well. In this work, the error distributions were put in by hand and also just assumed to be Gaussians with no parameter dependence. So that's where we got involved in generalizing this, and the generalization, although we had more complicated schemes in mind when we started off, ended up with something actually pretty simple, and that is just the following: produce multiple realizations of the summary statistic at each design point, and then model the distribution of, for example, the power spectrum at each design point as a multivariate Gaussian. Now, this is not saying that this is not as restrictive as it seems. For example, this is just saying that the distribution of the realizations is Gaussian. It's a different thing entirely. To figure out what is the probability of the mean power spectrum given your data, that could be non-Gaussian. This is just saying in a forward simulation that scatter in the power spectrum is Gaussian. Then we need a way to parameterize the covariance matrix for this Gaussian. And then we treat these parameters just as the mean was treated, as resulting from a Gaussian process, in order to do the interpolation. We've done a very simple application so far, just taking a power spectrum that's a power law, and realizing some data from that with these errors, where the variance in the power spectrum just goes like the square of the power spectrum, and actually even diagonal covariance, and 32 bands of K. And so in this two-dimensional space, we looked at first, well, probably second, but what I'm going to show you first is a 7-point design result. So this is just 7 points in our two-dimensional space. And so the black is the exact result, the dashed line. The red is the Gaussian process run on this 7-point design. And the blue is also for the 7-point design, but where the parameter dependence of the covariance is ignored. So we're just assuming that the covariance matrix has no parameter dependence. So you see that, at least in this case, that parameter dependence of the covariance is important. So what's plotted here are the posterior distributions for those two parameters, for the amplitude and for the power law index. And so some things to point out. One, that you get the wrong thing if you're ignoring the parameter dependence of the covariance matrix. Two, you're actually doing not too poor, not horribly, approximating the exact with the 7-point design. You are getting some increased width, and that's propagating this interpolation errors, at least widening this out some. This bump we've traced back to this is the Gaussian process doing particularly poorly at low values of alpha, because it's actually having to extrapolate, do some significant extrapolation since there's only 7 points. And then the 30-point design things, the red and the black converge pretty well. And I don't have the blue point on here. So this is not very interesting data. Possible applications for more realistic data would be combining 2-point and 3-point functions in a manner that takes correlations between them into account. This is certainly difficult to calculate analytically, something that if you want to do very accurately, you probably are forced to using simulations. Also, another way to extend the framework in the more interesting cases is to incorporate systematic errors in the following way. Place the systematic error parameters on the same footing as the cosmological parameters. So if you can develop a systematic error model that's parametrized, then you can include them in your parameter space and run this, choose this design over this larger parameter space. And that has the following benefits. Well, it incorporates the effect of the systematic errors on the mean of the summary statistics, and it also folds in the uncertainty that's due to them, and that'll arise when you compute marginal distributions of the cosmological parameters, marginalizing over the systematic error parameters. And it's possibly a more efficient way of doing it than just Monte Carlo drawing draws from the systematic error parameters. So the importance of the parameter dependence of the covariance matrix is very application specific. Where you have data that with very small error bars, it's probably not very important. But it's actually not any more expensive. If you have to do the Monte Carlo simulations to at least understand your covariance matrix at some point in the parameter space, you can using our scheme, actually spread those out over your whole parameter space, and at least investigate whether that's a problem. So I'm not aware of any general framework that makes use of simulation data as efficiently as this one does. There are physically motivated fits to simulation data that are very useful, but it's difficult for getting errors out of them, and also not always applicable for non-standard physical models, so they just aren't as general. So I don't know, in the application to practical models, really how, in the end of the day, how useful this approach is going to be. I'm interested in pursuing it more, and certainly if we want to include simulations into our analysis in as efficient a way as possible, I think there's a lot of interesting ideas here. Thanks.
Okay, a few questions here, Martin.
What's the number of points that you need for this method? What's the scaling as a function of dimension?
I'm not sure. And that has to be very. What does it take for this to work? I mean, why does this work so well? One thing that's really important to it is the smoothness of the response function, right? So you're estimating something that's actually varying. It's a fairly smooth function of the parameters, and that's that's the basic reason you can get away with so few points. Keeping that smoothness, I don't know. Do you know anything about how this scales with the number of dimensions?
Well, much better than a uniform grid for stuff like if you're doing like kernel basis representation or something. But it's application specific. I mean, exactly how wiggly is your function and how active is it in different directions.
You still have to do interpolations and dimensions, right? So that would also still work for any really high dimension.
Yes, you need more points obviously, but it's a sort of scale with another non-ASCII physics application.
You've seen applications to how many dimensions?
Say 30 dimensions,
Uh-huh.
statistics literature.
Okay, yeah, Gary?
I didn't quite understand how you get the distribution of the summary statistic when, when you did the CMP case, the summary statistic was deterministic.
Right.
But from an n-body, it's a random variable
Right.
on each realization. So I didn't quite understand how when you go to a certain place in the parameter space, you interpolate the full distribution.
So, there. Right. So in the n-body case, we're modeling the power spectrum from each simulation as something with a mean and a covariance.
So it's assumed Gaussian.
So yes, the scatter, going forward simulation, the scatter from one point in parameter space in the statistic is assumed to be Gaussian. And yeah, you could switch to a mixture of Gaussians and fit those parameters.
And what do you do for each simulation that you use for each of these points? Do you run an n-body code with different cosmologies at the same random basis, or I'm not sure.
No. You change the random phases.
Okay.
So yeah.
So that's where you're probably getting.
Yeah.
You could just get a set of random realizations at some points in parameter space. You could have several realizations at one point or scattered around. And then it conditions on the individual realizations under the assumption that they're multivariate.
So it's
But you're mixing, when you change cosmology, if you change the random phases, you're mixing the dependence on the cosmological parameters, which the dependence on the randomness.
Just these
It-
reflections somehow.
So you're mixing these two things are different. So I'm still a bit
No.
confused.
Well, yes, they are different. But what we're doing is
There is some assumption
the
there.
the initial conditions are always drawn randomly, and they're different from one point in parameter space to another. We, given that, and our model that this is at each point, the resulting power spectrum has a Gaussian with a mean covariance. We now have our distribution for those means and covariances given the simulation data.
Once your particular simulation can be dominated by cosmic variance.
Right, but how does your answer know when you go from when you interpolate, how much of that dependence is due to changing cosmology, and how much is due to the fact that you are changing from realization to realization, which will reflect the distribution of your statistics.
Right.
So somehow,
That's
That's
exactly
the thing
the
I-
distribution we want to model, actually. In a sense, it's a two-tiered Gaussian, in that the realization of the power spectrum band powers from the simulation is Gaussian. And then the parameters of that distribution of the power spectrum realizations are themselves modeled as Gaussian processes. So
in the neighborhood of your chosen
Right. Yeah.
So, right, when you draw your emulated point, it has a random component.
That's
that
right.
you draw from a Gaussian, the size, the covariance matrix of which you determine by basically doing a maximum likelihood fit, or some kind of fit to the points in that neighborhood.
Well, you actually,
The trials in that neighborhood.
yeah, in the parameter estimation, you actually jointly sample the parameters that are controlling this interpolation and the thing you're interested in,
So
right?
like
Or even going to the parameters that are controlling that.
So
Right?
you would have trouble, for instance, with very low L multipoles where the distribution is not Gaussian.
Well, not as much trouble as you'd think, though, because at least we're capturing the major. You know, it's nowhere near as bad. You know, so let's say we've got the quadrupole variance C2, right, and probability of C2, and let's say that the best fit observations down here, and now okay, if I did simulations assuming that C2 has this value, you know, then I'd get some spread like this. When the actual posterior, you know, looks like this, and we would capture a lot of this because we would be doing forward simulations also from here, and noticing that sometimes when you're out here, you scatter all the way down to here. You know, so I mean, well, at least you know, that the variance is much larger out here than it is here.
But it would have to be a Gaussian.
Each of these would have to be a Gaussian, right? Yeah.
Alright. Any other question? Okay, if not, let's thank Lloyd again. So, if you exit the building, you cannot get back in because the door works only in one direction at this time. So if you still need internet, you